Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone. In this lecture video, we will be discussing about absolute convergence, conditional convergence, ratio test, and root test. So for our first definition, as you can see here, uh, how to determine if the series is absolutely convergent. So you're given an infinite series of this form and is said to be absolutely convergent if the series, if you take the absolute value and this new series is convergent. If this series here is not convergent, then the original series is convergent, this one, then the series is called a conditionally convergent. Okay, so let's try to have an example to illustrate these two definitions. Okay, here example, let's say this color blue. Example, um, determine if the following series is absolutely convergent or not. Okay, so this is our problem number 1. Summation of -1, sorry, to the n times 1 over n to the 3 halves, where n starts from 1 to positive infinity. So remember that the question is to determine if the series is absolutely convergent. Okay, although that this the given series falls, you can solve this using uh, alternating series test, but the question is you are going to determine if this series is absolutely convergent or not. Okay, so solution, the given series uh, will be absolutely convergent if the series, this one, summation of uh, so just take the absolute value, use the definition, sorry, to the n 1 over n to the power of 3 halves, and starts from 1 to positive infinity, is convergent. Okay, so let's try to show that this new series now, which you take the absolute value of the n term, this is our a sub n, is convergent. Okay, so now let's try to simplify this series. Summation of 1 over n to the 3 halves. This will become, notice that this is absolute value and our n starts from 1, and we know that when you take the absolute value of a negative number, and a positive number is always positive, so that's why this is equivalent to n to the 3 halves, and starts from 1 to positive infinity. Okay, so as you have noticed, this new series now, this one is a p series. Okay, so let's denote this as uh, asterisk I star. Okay, uh, we have the series in star is a p series with p which is equal to 3 halves. Okay, therefore, or uh, it is it is convergent. Okay, so we show that the series with the absolute value sign is convergent. Okay, so therefore the original series, therefore the uh, original series summation of negative 1 to the n, 1 over n to the 3 halves, n is equal to 1 to positive infinity, is absolutely convergent. Okay, so moreover, as you can see in the definition, uh, after the definition we have a theorem, and it says that if the series is absolutely convergent, then the given series or the original series is convergent. Okay, so that's how you are going to uh, show that the given series is convergent. um, this is helpful if the given series is an alternating series. Okay, so you will not you don't need to use the alternating series test. So all you have to do, if the given series is an alternating series, then show that it is absolutely convergent, and then after that you can conclude that the original series is convergent. Okay, so since we are asked that we are asked to show that the series is absolutely convergent, so therefore we have to end our solution uh, with regards to the what is being asked in the problem. Okay, so let's try another problem. uh, Problem number 2, this one, summation of negative 1 to the n plus 1 times n factorial over 2 to the n, where n starts from 0 to positive infinity. Okay, again, solution. The given series will be absolutely convergent if the series summation of this one, negative 1 to the n plus 1 n factorial over 2 to the n, where n starts from 1 to, not from 0 to positive infinity, is convergent. So let's try to, can we move this one, is convergent. Okay, anyway, so let's try to solve this new series with absolute value uh, by some other test. Okay, so let's wait. Now let's try to simplify this series here. Negative 1, absolute value of negative 1 to the n factorial times n factorial over 2 to the n, where n starts from 0 to positive infinity. And as you can see, our n starts from 0, so therefore if you substitute 0, 1, 2, 3 and so on and so forth, this is always positive. This one is always positive, and the absolute value of a negative number is positive, so this will become n factorial over 2 to the n. N starts from 0 to positive infinity. Okay, this is the simplified form of this expression on the left hand side. So what should we do here? Notice, okay, so let's denote this as sharp. Okay, equation sharp with a circle. Okay, okay, by RROG topic. Okay, RROG is relative rates of growth. We discussed it before. The limit of n factorial over 2 to the n as n approaches to positive infinity is positive infinity. The reason for this is n factorial is much faster than 2 to the n. Okay, so since the reason is, since 2 to the n is slower than n factorial. Okay, so this is our previous topic. So therefore, thus by divergence test, okay, by divergence test, summation of n factorial over 2 to the n, n starts from 0 to positive infinity, is divergent. Thus summation of absolute value of negative 1 to the n, n factorial over 2 to the n, n starts from 0 to positive infinity, is divergent. Okay, so since it is divergent, we cannot yet conclude that the original series or the given series is conditionally convergent. We have to show it first by some test that the given is uh, convergent or not. Okay, so moreover, uh, let's uh, let's show that the original series or the given series is convergent or not. Okay, so let's wait for the program to respond. Okay, moreover, let's show that the uh, given series summation of negative 1 to the n times n factorial over 2 to the n, where n starts from 0 to is convergent or not. Okay, so what method are you going to use to show that this given series is convergent or not? So let's pause for a moment and think. Okay, since I've told you that to pause for a moment, I know that you have now an idea on how to solve this series. So this is a alternating series, so therefore we will use the alternating series test uh, by using AST. We have, so first is we have to show, so this is our an, so clearly a sub n, which is equal to n factorial over 2 to the n, is greater than 0 for all n greater than or equal to 0. Okay, letter p, let's show that a sub n is decreasing. Okay, as you notice here, this one, a sub n, must be greater than a sub n plus 1, or this is equivalent to a sub n, which is over n plus 1, which is greater than or equal to 1. Okay, so let's plug in. We have n factorial over 2 to the n divided by n plus 1 factorial over 2 to the n plus 1. Is this greater than 1? Okay, so let's wait. Okay, let's simplify this. This is n factorial over 2 to the n times 2 to the n plus 1 over n plus 1 factorial. Okay, is this greater than 1? So simplify again. This is 2 to the n times 2 over n plus 1 times n factorial. Is greater than 1. So we have to cancel this one here, and then finally uh, we have 2 2 over n plus 1 greater than, is this greater than 1? As you can see, when n is equal to 0, it's true. When n is equal to 1, this becomes false. So 2 to the, therefore 2 to the n plus 1 is not greater than 1 for all n greater than or equal to 0. Therefore, p sub n is not decreasing. Okay, so as you can see, it fails to hold the alternating series test. You can do further investigation about the limit, and as you can see before, uh, the limit of a sub n is positive infinity, and again it violates the third condition of the alternating series test. Okay, so let's wait. So if you want to continue, you have to show that the limit of a sub n is 0. However, the limit of this the a sub n is positive infinity by RROG. Okay, relative rates of growth. So therefore, it violates violates the second and third condition uh, condition of the alternating series test. Therefore, the series, this one, n factorial over 2 to the n, where n starts from 0 to positive infinity, is divergent. Okay, so as you notice here, the series is not absolutely convergent. It is also not conditionally convergent. Okay, so let's make a conclusion here. Let's wait. Okay, so as you can see, the original series is divergent by AST. So you can only conclude that the series is conditionally convergent if by the given test the series is convergent. But unfortunately, in this situation, the series is divergent. So finally, we can conclude that the original series or the given series is divergent. So let's end this we call this one example. Okay, so in the next topic, we will be talking about the ratio test. So the just give you the idea. The ratio test is used to show that the series is absolutely convergent or not, by not using the definition. Okay, so that's how you are going to use the ratio test. But remember here, let's go back to our definition. So please remember here this one. Let's move up. Okay, is to remember that in order for the series to be absolutely convergent, the absolute value the one with the absolute value you are going to compute, if that series is convergent, then you can say that it is absolutely convergent. Okay, so but do not lose hope. After that, if the absolute value is not convergent, go back to the original series and then test whether the series is convergent or not. If the series is convergent, then you can conclude that the original series is conditionally convergent. But if not, then finally the original series is divergent. So for this theorem, it says that if the original series is absolutely convergent, then uh, meaning to say that if you take the absolute value, the series is convergent, then the original series is convergent, and it satisfies this inequality here. Okay, so this is how beautiful the definition of the absolute convergent is. So this is the ratio test. So as you can see here, this test is used to show that the given series is absolutely convergent or not, uh, without using the definition. Okay, for the first theorem 1 here, just take you have to let your a sub n, this one which is known to be non-zero, your a sub n, then just take the limit of this expression here, and if the limit is less than 1, then it is the original series is absolutely convergent. But if it is greater than 1 in number 2, or if the limit is positive infinity, then the series is divergent. And if it is equal to 1, then you have the conclusion is this one: no conclusion regarding convergence may be made. This is how you are going to use the ratio test. For the root test is needed if you have a problem that involves this one, the symbol in truth. Okay. If there's a problem where, or a given, or an exercise where there is a presence of the n truth, then you will use the ratio test. And again, it is the same as the ratio test. Okay, so let's have an example for this theorem. Let's have an example here. Let's try number 1. Let's try this problem, this one, and we know that this is absolutely convergent by using the definition. Okay, this is absolutely convergent, therefore this series is convergent also. Okay, let's try to answer that using ratio test. Okay, for our first problem, determine if the following series is absolutely convergent or conditionally convergent using the ratio or root test. So as we can see, this is our problem before, and we show that this is absolutely convergent using the definition. So let's try to solve this problem using ratio test. So solution, this one. As you can see, we have to let a sub n, and notice also that a sub n is non-zero, okay, for all n. So as you can see here in the definition, okay, we have to let a sub n and then show that it is non-zero for all n, and then after that get the limit. Okay, so we have to wait for the program to respond. So here we have what happened. Let a sub n to be equal to this sorry, 1 over n to the 3 halves. Okay, clearly a sub n is non-zero for all n greater than equal to 1. Okay, non-zero means it is negative or positive but not equal to 0. Okay, so take the limit, then the limit of the absolute value of a n plus 1 over a sub n as n approaches to positive infinity is equal to this one. So we have n plus 1 here, so we have negative 1 to the, replace n by n plus 1, so we have 1 times 1 over n plus 1 to the 3 halves divided by a sub n, which is negative 1 to the n times 1 over n to the 3 halves as n approaches to positive infinity. Okay, so simplify. Notice that we can cancel out negative 1 to the n. This one here, as you can see, this will be, can we have another color? Okay, so let's wait. This factor here, this one can be simplified as negative 1 to the n times negative 1. Okay, exponent is 1, so we can cancel out this one here, and then what is being left here is, as you can see, we have negative 1 times 1 over n plus 1 to the 3 halves times n to the 3 halves over 1 as n approaches to positive infinity. Okay, so as you can see, this is absolute value, so the absolute value of negative negative 1 is positive 1. And please to remember that this is inside of the absolute value is a product, so we can write it in this form, times 1 over this one, n to the 3 halves over n plus 1 to the 3 halves as n approaches to positive infinity. So this is positive 1. Okay, so let's wait again. Okay, this is positive 1. So what will happen here, we have limit of As you can see, this is always positive as n approaches to positive infinity, so this will become uh, this one n over 3 halves n plus 1 to the 3 halves as n approaches to positive infinity. So let's simplify this further. This will become the square root of n cubed over the square root of n plus 1 cubed as n approaches to positive infinity. And then finally we can combine the numerator and denominator. This is okay, as n approaches to positive infinity. And finally we have the, I think we can write it in this form, n over n plus 1 raised to the power of 3, and then I guess we can write it in this form, limit of n over n plus 1 as n approaches to positive infinity, and then if you take the limit of n over n plus 1, so all you have to do is to multiply both sides by 1 over n over 1 over n. The denominator becomes 1 over the numerator is 1, but the denominator is 1 plus 1 over n, and the limit is 1. Okay, the limit is 1. So can we choose another color here? Okay, the limit of the radicand, this is very familiar, n over n plus 1 as n approaches to positive infinity, 1 over n. This is limit of 1 plus over 1 plus 1 over n as n approaches to positive infinity, and this is 1. So as you can see, this is square root of 1 cube, which is 1. And as you notice, the limit is equal to 1, therefore your conclusion is the ratio test fails. Okay, so since the limit of the absolute value of a sub n plus 1 over a sub n as n approaches to positive infinity is equal to 1, but as you notice here, do not conclude that the sequence the series is divergent. Okay, do not conclude. You can still continue since the series negative 1 raised to power n over 1 over 3 halves where n starts to 1 to positive infinity is convergent. Okay, convergent. This one absolute value by previous uh, solution. Okay, the series, this one 1 over n to the 3 halves, and starts from 1 to positive infinity is absolutely convergent. Okay, so what are the things that we learned from this example? As you can see, the limit of the absolute value of a sub n plus 1 over a sub n as n approaches to infinity is equal to 1. So meaning to say that the ratio test fails. After that, do not conclude that the series is what they call this one, conditionally convergent. Okay, uh, if ever that the limit is equal to 1, then use the what they call this one, the definition. Okay, so anyway, let's have another example. Example number 2 here. Example number 2, this one, or letter B. Letter B. Let's try to solve the second problem that we did. This one, we show that this series is let's look at our previous solution. This is divergent. Yes, this is divergent. So let's try to show using ratio test if this is really divergent. Okay, anyway, let's wait. Okay, so last time we show that, as you can see here, this one. Okay, this series is divergent. So let's try to answer this using the ratio test. Okay, solution. Let a sub n to be equal to this one, negative 1 to the n plus 1 of times n factorial over 2 to the n. Okay, so clearly a sub n is non-negative for all n greater than or equal to 0. Okay, so let's try to evaluate the limit of a sub n plus 1 over a sub n as n approaches to positive infinity. Okay, so this one, the numerator is negative 1 to the n plus 2 times n plus 1 factorial over 2 to the n plus 1. Okay, so replace n by n plus 1. The denominator is a sub n, so we have negative 1 to the n plus 1 times n factorial over 2 to the n. Okay, so simplify. Okay, we just have to wait for the program to respond. So notice here that this is equivalent to, okay, this is negative 1 to the n plus 1 times negative 1 times n plus 1 times n factorial over 2 to the n times 2. So you have to reciprocal the denominator. So we have 2 to the n, negative 1 to the n plus 1 times n factorial as n approaches to positive infinity. So what happened here? So we can cancel out this one also, and so also. Okay, and then the absolute value of a negative is positive, so we have n plus 1 over 2 as n approaches to positive infinity, and we know that the limit of this function is positive infinity. Okay, so if you look at the theorem of the ratio test, if the limit of the absolute value of a sub n plus 1 over a sub n as n approaches to positive infinity is positive infinity, therefore the series by ratio test, the series is divergent. The series, this one, to the n plus 1 times n factorial over 2 to the n, and starts from 0 to positive infinity, is divergent. Okay, so let's try to look at the theorem above. Okay, let's wait for the program to respond again. Okay, let's move upward. Okay, let's go back to the theorem. As you can see here, if the limit is positive infinity, the series is divergent. Okay, so I think the ratio test is much easier to show that the given series is divergent or absolutely convergent than the, how to call this one, the definition. Okay, I guess that's all. Maybe let's have an example of on how to use the ratio test. Okay, let's try this example to illustrate the root test. Summation of e to the 3n over n to the n, where n starts from 1 to positive infinity. So as you can see here in this example, there is no factor. Uh, the factor negative 1, quantity of negative 1 to the n plus 1. So still you can use the ratio test or the root test to this kind of problem. Okay, anyway, so let's try to solve this using ratio test. No, ratio by root test. Okay, root test. Okay, so again, uh, we have to let a sub n to be equal to e to the 3n over n to the n. Okay, so I think I forgot to look at the assumption of the root test. So let's pause for a moment. Okay, clearly a sub n is non-zero. All n greater than or equal to 1. So now take the limit of the nth root of the absolute value of a sub n as n approaches to infinity. So as you can see here, okay, substitute e to the 3n, sorry, e to the 3n over n to the n as n approaches to positive infinity. Okay, let's simplify. This is equal to, okay, notice here that we can now remove the absolute value since your n starts from 1 up to positive infinity. This is always positive, so remove the absolute value and then simplify. So we have to express it in this form. Okay, I know that this is very familiar algebra. Okay, so again, let's wait for the program to respond. Okay, let's move up. Okay, this is equal to the limit. Okay, we can cancel out our n here. The limit of e to the 3 over n as n approaches to positive infinity. So this is equal to, as you can see here, a cube times the limit of 1 over n as n approaches to positive infinity. And we know that this is 0. So this is 0 times e cube is 0, which is less than 1. Okay, so therefore the given series is absolutely convergent. So therefore, let's put it here. Therefore, the series, the given series summation of e to the 3n over n to the n, where n starts from 1 to positive infinity, is absolutely convergent. Absolutely convergent. Also in the theorem, if the series is absolutely convergent, therefore the series is convergent. Hence a convergent series. Okay, absolutely convergent. Okay, so let's try to answer this problem using ratio test, and we shall see that it is more convenient to use root test than the ratio test. So let's have another solution using ratio test. Okay, another solution, solution using ratio test. Okay, this is to show how useful the root test in solving the previous problem. Okay, so again we have to let a sub n to be equal to e to the 3n over n to the n, and clearly a sub n is non-zero for all n greater than or equal to 1. And now the limit of a sub n plus 1 over a sub n as n approaches to positive infinity, this is equal to okay, notice the numerator is we replace our an here or n here to n plus 1, so we have e to the 3 times n plus 1 over n plus 1 to the n plus 1. Okay, the denominator is e to the 3n over n to the n as n approaches to positive infinity. Okay, let's simplify. So what will happen here is we have e to the 3n times e to the 3 over n plus 1 to the n times n plus 1 times reciprocal n to the n over e to the 3n. Okay, so we can cancel out e to the 3n here, and then what remains is this expression e to the e cube n to the n, and this denominator here. Okay, let's wait for the program to respond. Okay, we have e cube times n to the n over n plus 1 to the n times 1 over n plus 1 as n approaches to positive infinity. And as you notice here, this is a product, so we can distribute the limit. The limit of the constant is a constant times the limit of n to the n over n plus 1 to the n as n approaches to infinity, and the last factor, we have the limit of 1 over n plus 1 as n approaches to positive infinity. Okay, so this is a constant. Okay, let's try to use another color. Okay, this one is 0, and this one is e to the 3. Okay, constant. So the answer here is e cubed times, we are not sure what is the limit of the second factor, so let's leave at that. And the third one is 0. Okay, so if it happens that the middle factor is infinity, and then we have a problem here. So anyway, let's compute the second factor. Okay, let's wait for the program to respond. Okay, let's look up. Okay, let's compute the limit of n to the n over n plus 1 to the as n approaches to positive infinity. Okay, notice that we can rewrite this in this form: n over n plus 1 raised to the power of n as n approaches to positive infinity. So as you can see here, this is very familiar. Just recall your calculus 3 subject. We can write this in this form. We have to let L to be the limit of n over n plus 1 raised to the power of n as n approaches to positive infinity. So ln both sides. So we have the limit of ln n over n plus 1 raised to the power of n as n approaches to positive infinity. Notice that, sorry, this is limit. Okay, correct that to 1 liter. And this is limit of n times ln of the quantity n over n plus 1 as n approaches to positive infinity. Okay, so in the form for this expression here, the left hand side is clearly what happened. Okay, let's erase this first. Okay, this is ln of n. Clearly on this side, this is an indeterminate form. So we have infinity plus infinity times 0. Okay, so the limit of ln of n over n plus 1 as n approaches to infinity is 0. So let's convert this to 0 over 0. So this will become ln of n over n plus 1 over 1 over n as n approaches to positive infinity. Okay, so clearly this form here is 0 over 0. So we can use L'Hopital's rule. Okay, we have ln of L. This is get the derivative of the numerator and also in the denominator. So we have negative 1 over n squared, derivative with respect to n. This is 1 over n times n plus 1. And we have a quotient rule. Okay, square the denominator. Denominator times the derivative of the numerator is 1 minus numerator times the derivative of the denominator, which is 1. Okay, so simplify. This is ln of L, which is equal to the limit, say, let's put it right here. Okay, let's wait for the program again to respond. Okay, let's simplify. This will become the numerator becomes n plus 1 over n times, this becomes n plus 1 squared, and then this, the numerator is 1, okay, over negative 1 over n squared. Ln of L, this is the limit of, so we can cancel out n plus 1 here, and then reciprocal, we have 1 over n times n plus 1 times negative, sorry, this is n squared over negative 1 as n approaches to positive infinity. So cancel out, and then we have n over n plus 1, and we have a negative here, approaches to positive infinity. Okay, so we can multiply both sides by 1 over n, and then finally we have the limit of the negative of 1 over 1 plus 1 over n as n approaches to positive infinity. Okay, so let's try to write it here. Ln of L, which is limit of, okay, sorry, there's something wrong, let's wait again. We have ln of L, which is equal to, we can now evaluate this limit, which is negative 1 over 1 plus 0. So we have ln of L, which is negative 1. So this is our L here is e to the negative 1. So therefore the limit of n to the n over n plus 1 to the n as n approaches to positive infinity is 1 over e. Okay, so as you can see, this is a constant, so meaning to say, if you recall our discussion above, so we have e to the 3 times 1 over e times 0, so the answer is 0, so which is less than 1. Okay, so again, let's wait for the program to respond. Okay, let's move upward. So let's go back to problem. So the answer here is 1 over e. So this is finally 0, which is less than 1. Okay, so by ratio test, we can show that by ratio test, the series is absolutely convergent. Okay, so if you compare the two tests, as you can see, ratio test is longer, than the root test. So now I believe that you already know the usefulness of on how to use the root test than the ratio test. Okay, so I guess let's end our topic here. Okay, before I forgot, let's tackle this probably last topic, rearrangement of series. So as you can see, this topic is in relation to our previous topic, which is absolute uh, convergence and conditionally convergence. So as you can see here, if you rearrange the term of the series, the question is it the sum will be the same? So let's try to answer that in this topic. So as I've said, this is in relation to the absolute convergence and the conditional convergence. Okay, so if you remember, uh, a a finite sum, for example, a finite sum such as this one, uh, 1 plus 7 minus 3 plus 20 uh, plus 6 minus 2. uh, as you can see, can be uh, can be rearranged without uh, changing the value of the sum. Okay, so you can do that in the finite sum. So how about the if you are given an infinite series? So this is not necessarily true uh, uh, with with regards to an infinite series. When you say uh, it depends on whether the series is absolutely uh, convergent or conditionally convergent. Okay, so this is the answer to the question. It depends on the series if it is absolutely convergent or conditionally convergent. So here, if your series is proven to be absolutely convergent, then rearranging the terms, the sum will be the same. Okay, but for conditionally convergent series, if you rearrange the terms, then what will happen is you will have a different sum. Okay, so let's put it in writing. If a series is absolutely convergent, then its terms can be rearranged in any order without changing the value the value changing the value of the sum of the given series. Okay, if a series, this is for the conditionally convergent, if a series is conditionally convergent, then each terms can be rearranged to give a different sum. Okay, different sum. Okay, so I guess let's have an illustration for the second. Alternating harmonic series converges to negative ln2. Okay, as you can see below, summation of -1 to the n starts from 1 to positive infinity times 1 over n. So if you try to expand this is -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6 and so minus minus 1 over 7 plus -1 to the n times 1 over n and so on and so forth. Okay, this is convergent and its sum is negative ln2. Okay, question is rearrange the series to produce a different sum. Okay, so please do remember that this series is a conditionally convergent series. Okay, since if you take the absolute value it becomes a harmonic series, and as you can see a harmonic series is a divergent series. But the original, if you use the alternating series test, or maybe you can use the ratio test, you can show that it is convergent. Okay, anyway, it's up to you to show that this series is conditionally convergent. So solution, consider the rearrangement below. Okay, so we have summation of -1 to the n times 1 over n, where n starts from 1 to positive infinity. Okay, So first is you have to expand this is the expansion. Try maybe expand to uh, maybe more than 10 terms here. But anyway, uh, this is the following rearrangement. For this one, just factor negative 1 here, so this is 1 minus 1 half plus 1 fourth minus 1 third minus 1 sixth plus 1 over 8 minus 1 fifth minus 1 over 10, and so on and so forth. Okay, and let's move up. This will become negative 1 half plus 1 fourth minus 1 over 6 plus 1 over 8 minus 1 over 10 plus 1 over 12 minus 1 over 14, sorry, plus that. Okay, so as you can see here, factor out negative 1 half, and what remains here becomes 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 sixth plus that and so on. And as you can see, if you evaluate this one, this is ln2. Okay, so what is the conclusion? By rearranging the terms, we obtain a different sum. This is because the given is a conditionally convergent series. Okay, so if the series is a convergence, the series is an absolute convergent series, then we have the sum will not be affected. Okay, so I guess that's all. So I hope you understand the method on how does the rearrangement of a series works. Okay. Okay, before I finally say goodbye to our part 1 of chapter 8, which is entitled polynomial approximation, sequences, and infinite series, let me remind you that the strategy on how to apply the test that we discussed so far. We have, as you can see, 10 tests. Let me enumerate. Number 1, we have the divergence test. Number 2, we have the geometric series, and then we have telescoping series, and then we have the P series, alternating series, integral test, root test, ratio test, and also we have direct comparison and limit comparison test. Okay, all in all, we have 10 tests on how to show that the series is convergent or not. And as you have noticed also, if you practice more in the problems or exercises in the book of Larson, Lighthold, and many other calculus book, the skill in choosing and applying the various tests will come only uh, with more practice. Okay, I will give you a guidelines. Just I'm not going to write this. There are guidelines for testing a series for convergence or divergence. First is all you have to do is ask this to yourself: does the end term approach to zero? So that's the first one is what we call the divergence test. If not, the series is divergent. Okay, and then after that, if number that first guideline will not work, then the second is ask yourself if the series are of special types. So meaning to say it is a geometric series, if it is a P series, or telescoping, or alternating. Okay, and then uh, apply the integral test, and then after that maybe apply the root test or the ratio test. Okay, and then finally uh, use the direct comparison or the limit comparison test. Okay, so there are in some instances more than one test is applicable for a given problem. However, your objective is to choose the most efficient test. Okay, please remember that one. Okay, so it doesn't matter what test you are used as long as it will not violate the assumption of the given test. Okay, so thank you so much everyone for listening. So don't forget to subscribe to my channel, and please click that red button below and the bell button also. Thank you so much for watching.